Okay, so the lecture today is a different topic. So yesterday we saw how to, it's part of something that we call causal modeling. It's causal discovery, is how can you understand the underlying mechanisms. Today is about understanding the effect size. So it's computing or quantifying the effect once you know that there is a causal effect. So the outline, I think I also have to, so the outline here is, I will define, you saw this in the first lecture, but I will define again what is a structural causal model, it's not structural, structural causal model. Then I will also define properly what are causal Bayesian networks, which is the same as the same name as is a synonym for causal diagrams. Also, we will first start checking or evaluating the effect of a causal direction. Once you know what's the causal diagram, so giving a causal diagram. So I'm using this approach because, like this outline, because this is how the theory evolved. And still, in many situations, you have the causal diagram from prior knowledge. Then inside of this topic, we will first see what are the techniques for Markovian models. Markovian models are models where there are no latent confounding, right? So this is something we saw last time. Then we will move to semi-Markovian models where there are several graphical criteria, for example, parent criterion, backdoor criterion, also front door criterion. We will see all of this. Those are just, so before the criteria, they are graphical approach where basically so they are condition. So it's a sufficient condition to have identification, but not a complete condition, right? So general tools include, which are complete in the sense that if you apply those tools and you don't get an answer, you don't have identifiability. So those includes do calculus and ID algorithm. We will see if we have time, I will probably go through examples of do calculus, but the ID algorithm, unfortunately, there's no time to go over it. We will see just an example. Then I end with some advances in the field. For example, how can you do effect identification without the causal diagrams? So last time we learned some algorithms to learn the Markov equivalence class. For example, a PEG is a representation of the Markov equivalence class that you can obtain through the ESSAI algorithm. So here you can identify causal effects from this representation. So it will be a completely data-driven approach. And in the end, we'll discuss some challenges that we still have in the field. Okay, so that's our outline. So prediction versus effect of intervention. So this distinction is really important because it's what help us to define what's a causal effect. So let's see an example. So suppose that I give you this task. Okay, can I guess? It's just a guessing problem here. Can I guess the size of a fire by observing the number of firefighters? What do you think? Do you imagine that you look through the window and there are like 100 firefighters there? Can you guess what's the size of the fire there? It's probably very big, right? So you can guess. You can even collect data. So for example, we have two variables, number of firefighters in action plus the size of the original fire, right? You can use any statistical tool here, could be even linear regression. And then you see a very high correlation. In this case, we see the correlations being this correlation. So the fact that this correlation is different than zero. Yeah, it's not working. Anyways, the fact that the correlation there is different than zero implies that X is a good predictor. So you can actually use this variable to help in the prediction of the size of the fire. However, this this is just the definition, right? So the probability of y given x being different than the probability of y implies this correlation. And this probability distribution is something that we call observational probability distribution. It's just a name. And it's observational because you use observations to just see how well a probability is changing given observation. So the probability of y changes once you observe the value of x. So in this case, we have a positive correlation. So in this case, we can say that if we have more firefighters, this means that we have a bigger fire, and fewer firefighters mean a smaller fire. Okay. The problem here is like people start jump on causation. So once you see this, maybe you start having ideas about decision that you can make some decisions about the But what do you think? It's like if we just reduce the number of firefighters, we dispatch fewer firefighters. Do you think this is going to reduce the number of the size of the fire or not? Obviously not, right? It's also red. I think the better of this is also not working. Do you mind if I continue? Or can you hear there? Okay. The guys. Okay. Let's wait. Hello, hello. Yeah, it's just working for a few seconds. Hello. The battery is really low. Hello. Extension is not here. Okay. There's someone, and there are 8 people. Hello. Some people in the call from here. There's no. Yeah, we know. So both of them are not working. Now I was trying to. Why is not working? The battery is low, and this is also red. It's the click is, yeah. This is also working. So this is working. One. Now it's not working. So. Sure. Hello? Oh. No, it's going to die. Hello? Perfect. So we are back. So you are even laughing, right? So why you are laughing? Why you know that this is not going to work? By experience, because you know the process, right? So you understand the underlying reality. You know that this is just, oh man, yeah. This is just that the size of the fire that determines the number of firefighters needed, not the other way around. So you know the process, you know how nature works and how firefighters work and so on. And that's a interesting example, because when it's something very obvious like this, we don't jump. But in other situations, you jump. You see the link of some food and then some disease, and then you just assume that maybe reducing the consumption of such a food you help you to prevent some disease. And of course, you cannot do unless you understand the underlying nature. So I think I jumped. Yeah. So here the causal direction is determined by the understanding of the underlying reality. So we need to know that, of course, we don't need to know all aspects of this underlying structure causal model, right? So the model of the reality. But the fact that we know the order of how these variables are one depending of the other, we can say if y, so in this case, y is not a function of x, right? So x is actually a function of y. So the fact that y is not a function of x means that x is not a cause of y. So to be a cause, you just need to be to have as the variable is a cause if this variable is an argument of the function, right? And so in other words, here x is not a cause of y, and because of this change in the number of firefighters through an intervention, so this is another important concept here. We want to change something and then expect some outcome. So that is first this notion that we are not just observing a variable, but we are changing this variable, and then we expect some change in the outcome. So the fact that we change the number of firefighters by an action won't change the size of the fire, because X is not a cause of Y. Okay, so this is the reasoning. This is how you define causal relationships. So let's try to understand better what is the structure causal model. You saw this already, but this is the most powerful knowledge that you can have to understand nature. So we assume that exists this model of reality, okay? So the structure causal model, as you saw in the first lecture, is just a tuple. You have 4 components. First, you have the set of endogenous variables. We will always call it as V. Those are the observed variables, right? So you also have other variables that are important in the mechanisms. And if they are not observed, we are just calling them exogenous, and we are representing with the set U. You'll be always like this. Also, we have the functions that determine, and you see here that we are only concerned on the set of variables V, that are the observed variables. So we expect that that exists a function that explains how Vi, which is one of the variables in the set V, how Vi is determined. And this is going to have as arguments so we represent as PA just the set of variables that are observed. Here, PA is a subset of V, but also you can have other causes that are just exogenous. So those are going to be in the set U. Okay, so those are sets. And then you have this probability of U. If you have everything like this, you have the full explanation about reality. We have this assumption that the model is acyclic, although we are also in the field relaxing this assumption, but the field started making this assumption. You saw this in many other fields. So a structure equation model is something very popular in statistics. Who have heard about a structure equation modeling here? Yeah. So this is very popular in statistics. Basically, they even call this as a confirmatory inference. But you see that we have to write here. We have to get the set of observed variables. Those are your error terms. And then you have to usually specify, of course, you don't know the parameters. The parameters you have to estimate, but you need to specify if it's a linear combination of which variables are affecting each of the variables. All here are linear functions. You have this recursive format in the sense that z doesn't depend on any other variable, x only depends on z, y depends on both, so it's recursive. You also have to specify the structure of the error terms. In this case, all they are normally distributed and they are independent of each other. All these assumptions you make because you need identifiability in the estimation of the parameters. But if you have this knowledge to construct what's the order of the variables, you know what's the parametric form of them, you know what's the distribution of the errors, you know everything. If this is true in the reality, then you have a causal model, right? So there's nothing to do. You just estimate the parameters are going to be your causal effects, that's it. But you have to specify a lot of things: pre-specified causal order, linear functions, normal distribution, Markovianity. The fact here that the error terms are independent of each other, if you are making this assumption, this implicitly is going to say that you are assuming causal sufficiency. You are saying that the correlations between these variables can only be explained by the observed variables, not through other variables. So you are assuming Markovianity here. And so that's all, right? So if you can write the full model, you can estimate the parameters. As long as this is true with the according to the reality, you are doing causal effect estimation. Very simple. Of course, we not always have this, and not always we want to make this assumption. So that's why the field is moving away from the level of structural causal model and going to the level of graphical causal models. So so imagine that you have the structural causal model, the functional causal model. This model implies a distribution. This distribution is the observational distribution. And from this distribution, you can, for example, answer questions related to prediction. So if the probability distribution here, you can just check what's the conditional probability of y given x, compare with the probability of y. And if they are different, this means that x helps in the prediction of y, or x is correlated to y in this case. And that's all you need to know, that after observing x, you have a better prediction of the value of y. Okay, and the correlation or the association between these two variables can be explained by these red parts here. Can be either because x is really a cause of y, so as an argument of the function, but can be also due to something that we call shared cause. So you see these two u variables, they are latent, so you don't observe. So they are present in these two equations, so they are shared. They cause both x and y. And this creates a confounding relationship. They create a spurious association. And so through correlations, only you don't know what's happening here, but it doesn't matter. As long as you have a correlation, you can do predictions after observing, right? But if your question is related to prediction after an action, which is denoted by this operator do in the field, it's just a hypothetical intervention. You don't need to run an experiment. It's just a notation for changing the x variable to a constant x. And in the model, you clearly see this by just replacing the equation of x by a constant. So if you have a model, just manipulate the model and you evaluate the equations. Because you have the model, you have everything. If you generate, if you get this model, this model implies a different distribution, which we will call interventional distribution under the intervention on x. And this probability which is just the implied probability of this model here, we will denote with this 2x after the conditioning bar. And this allow us to see if a variable is actually a cause of the other. So in this case, you see that after changing x, so after setting x to a small x, the function of y has nothing shared unless only the variable itself. So the only way to x and y x being helping at y in this situation if x is an argument. So all the measured confounders here, they were removed, right? So the only reason to see a change in the probability of y after doing an intervention is really if you have x as an argument here. So you can compare the probability of y in this model with the probability of y in this model. And if it's different, then x is a cause of y. So that's the way that we defined in the field. Questions related to this? Okay. So a causal Bayesian network is different from just a Bayesian network that we saw yesterday, because they don't only encode conditional independencies, but they encode causal and confounding relationships. So they have to actually correspond to these directions or these functional relationships that are coming from the structure causal model. So let's see how actually is defined a causal diagram or causal Bayesian network. So the structure causal model, you don't need to know. So I don't even write here what are the functions. It's just F. I only need to understand how are the variables connected, or which variables are arguments of the functions of the others. So one of the conditions here is that if we have Vi as an argument of the function of a variable Vj, Vj. So here's Fj is the function for Vj. So in this case, we add Vi as pointing with a directed edge to Vj. So Vi is an argument of the function of Vj. So in this example, we have, oh man, yeah. So in this example, we have, for example, B is an argument of C, A and D is an argument of B, so you can see here and so on. We only do this for the variables in V. So of course you have other causes or other arguments which are in the U set. If you were following this for every U, you would add all the variables like this. However, it's ugly. So people don't like this representation. So what we do, and the reason why we simplify is because all these error terms or these latent variables that are independent of these other variables, like the UA is affecting only A, UD is affecting only D. So all those variables that are not affecting two variables at the same time, we hide them. And the only part that's interesting for inference are those that are creating confounding. So we are going to replace this with a bidirected edge. So that's the meaning of a bidirected edge. So as long as two U's are either correlated or they are shared as arguments of two functions, we add this bidirected edge. Okay. All right. So a causal Bayesian network, then it's an encoder of structural causal knowledge, right? In contrast to Bayesian networks, which are encoders of conditional independencies. So yesterday we saw that factorization is implied, which is the factorization by the parents or by the extended parents. Here we have something more powerful, because if you know that this is a causal Bayesian network, then we can even factorize this interventional probability, not only the observational probability, but the interventional probability. And so if you have a ADMG as a causal Bayesian network, so this is the entire collection of all probability distributions given some do X for every X in the set V, it's going to hold this factorization. this factorization, which is called truncated factorization. You see that the difference is that X is no longer here as part of the product because X is fixed. So the probability of X being X is 1. So you eliminate this factor and everything else is again. So that's the only difference. This is going to be important. So you see this later again. But you know that there's the same idea. So every variable just depends on their causes. And then you have the probability of the U variables that they don't depend on anything. These causes can be either observed or unobserved, but it's just the product of every variable given the causes. Yeah. So the structure causal model induces some objects, right? So we just saw that it's really hard to have the functional relationships, but sometimes you can have objects that are induced by this model. So we all know we can get data from this model. So if you collect the data, it's coming from this model. This is one of the objects. Of course, there's laws of information. That's why we have the concept of Markov equivalence class. We have other objects. We have the observational distribution itself that could be even estimated given observational data. And we can have the causal diagram, which is more informative. You would need to use knowledge to understand the directions, like the example of the firefighters and the fire. You would know that this one affecting it's the firefighters, Y is being affected by the size of the X and not the other way around. So in many situations, you know how to get this diagram. And this is basically the least informative causal diagram once you know the direction, because you may allow any confounding between these two variables. It doesn't need to be just one variable, it can be a bunch of variables. It can be connected in very different situations, but as long as you cannot rule out the possibility of having other variables affecting X and Y at the same time. You just add this bidirected edge, and this is encoding these complex models as like a projection of these very complex models. In the interventional world, this is this right side of the slide here. We also have information that's lost once you have data, right? Or once you have it's very slow. We have data. We have the interventional distribution, which also could be estimated from data. And you could also draw your causal diagram that once you have this intervention, basically you have no edge pointing into X anymore because X is a constant. So all these confounding variables that were affecting X and Y at the same time are going to be just affecting Y, right? And so I think I'll give up on this. So randomized experiments is something that we know that is mimicking these interventions in the road, right? So how does this work? So a well-accepted way to assess this interventional distribution is through a randomized random trial. And I pointed here, I stressed here that has to be a perfectly realized RCT, because in many situations, you also don't control all the variables. You also don't have a perfect randomization of the experiment. But in this scenario where you have a perfect RCT, you can just see that the effect of this intervention is going to be, we usually have like a binary treatment. So you have two graphs. So the first one is receiving, for example, a placebo or X0 in this case. And this randomization, it basically cuts because you are controlling all the confounding and also randomizing the treatment. So it's cutting all, or minimizing the influence of all these confounders. So that's a kind of interpretation of randomized experiments. And from this diagram, you also, this diagram represents the system that has been manipulated. And if you collect the data from this, and then you estimate the probability distribution and get the expectation for this group, for example, you have exactly this, estimating this quantity here, which is the expectation of Y given do X equals to X0. In the other case, in other group, you can just apply, you can assign another treatment, like could be like a drug, and then there's the same effect. The randomization is going to minimize the effect of the confounding, and if you have data from it, you just get the expectation of this group. And then the causal effect, the average causal effect, is just the difference of these groups. So the point here is, if we have a way to minimize this confounding effect, we can just get the difference, and that's the causal effect. But can we always conduct randomized control trials? What do you think? What can happen? We saw an example last lecture about cell phones and cancer. Can you randomize in this situation the treatment? What's the treatment here? Could be the cell phone, and then let's make some group using a phone, another group is not using a phone. Let's wait 10 years, see if the person gets actually the cancer or not, but then you have to control all the confounders. So you need to enforce those people to use the same cell phone for 10. It's impossible, right? So you have several practical limitations. So I have here another XKCD comic, which basically compares what's a normal person and a scientist. So a person just tries something once. I don't know if it's hard to see here. It's just pressing a button, gets a shock, I guess. And then a normal person just say, I don't do this anymore. One sample is enough for it. But then a scientist say, no, I need to try more. So you need a sample. You need to try this several times. And even in this situation, you don't really know if this is experimental, because you are not randomizing or controlling so not even here we have a causation. But it's really hard. So you have to do experiments. You have problems regarding to ethics. You have practical limitations. You have logistical challenge. So you have many problems. So the question is, can we identify the effect without having experiments? And one of the approaches is just assuming that you have a causal diagram. So you have knowledge to construct this causal diagram. In this situation, you have this pipeline. So that's the classical pipeline for causal effects. So you start with a question, a research question. So what's the effect of X on Y? And this effect is just represented by this interventional distribution here, right? So once you have the distribution, you can get the expectation or whatever you want. But we also assume that you have knowledge about this underlying model, the underlying structure causal model, or the underlying reality. And this is always a projection. I always like to stress that you can have several variables here and here, other confoundings, but as long as you can reduce the model to have, like this confounding can be several variables together. But as long as you have some knowledge to represent this diagram, you can impose these constraints. And if you, so this is always through knowledge, right? And in the pipeline, this is called causal modeling, and can be also done by causal discovery, as we saw last lecture. I will show you how can you extend the entire pipeline in this situation. But and once you have observational distribution, you can just feed this input to an inference engine. I'm not going to break right now this box, but it's not black box as deep neural networks. There are several algorithms there. But you can use those tools to do effect identification. And those tools not always have a positive answer. Sometimes this knowledge that's represented in the input, for example, in this causal diagram, may not be sufficient to identify the effect, which means that you can have a no answer. But if you have a positive answer, this means that you have an expression that only depends on the observational distribution. So you see that these two terms, they don't have a do. And you can map, basically you can map every you can compute the expectation if you want, but you can map the available distributions that's coming from here to your research question, which is the interventional distribution. So if this mapping exists, it's because you have identifiability. And these tools are going to tell you this expression. You just give this as input, and then you add this as an answer. Once you have this formula, so this formula, you see that's depending on the observational distribution. Not always you have this available, right? So sometimes you have to get data as well to estimate this distribution, and then you just plug in here and then get the estimation. So we estimate the effect. Once you know the formula, you just estimate the effect by getting estimates for each of these terms. Okay? Questions related to pipeline? Okay. So what is a causal effect? So a causal effect is a quantity, any quantity that's derived by this probability that we call interventional probability. And this quantity is telling us how much Y changes due to an intervention on X. So you can have several definitions of causal effect. One very common definition is the average treatment effect. So it's the difference between two levels of the variable X. So this usually works for discrete treatments. You could also have, and here I'm just showing that given the probability, you can just apply the definition of expectation, and that's all, right? So as long as you have this probability, you can estimate the expectations, and then you get the difference. If you have a continuous treatment, then some people just define as the derivatives, the partial derivatives of this expectation. And this is also something that can be derived by the interventional probability, right? So usually the definition of causal effects depends on who is so in many situations, you see that let's compute the average treatment effect. So it's already defined by the setting. So if your treatment is discrete, usually they define like this or like that. But in the end, all you need is computing this probability. So in this lecture, I will not going to use any of these terms. I'm just looking for techniques to estimate this probability, because once you know this, you can just plug in this in the technique, and that's all. So what is the effect identification problem? So you don't need to read this right now. I'm going to give you the intuition. The intuition is the following. So suppose that you have a structure causal model, and this is your true model, and this is going to induce some causal diagram, and it's going to induce also a probability distribution. This is the observational probability distribution. Of course, we saw last time that there are many, many models that could induce exactly the same causal diagram and the same distribution. Effect identification has to be like a case where the interventional probability, which is the probability of Y given to X, is the same for any model, as long as they are implying the same causal diagram and the same observational distribution. So if for all these models that imply the same causal diagram and the same probability distribution, they have the same also interventional distribution, then you can get identification of the distribution. Another way to illustrate this is like this diagram. So in yellow here, you have all the models inducing the same probability distribution. In blue, you have all the models that are inducing a causal diagram. And as long as all models in this intersection have the same probability of the interventional probability of Y given to X, then you have a case that's identifiable. If at least one of the models is implying a different probability of Y given to X, a different interventional distribution, then since you don't know which graph is your true graph, or each model is your true model, you don't know, you don't know which model, the structure causal model is your true model, you don't know what is the expression. You don't have unicity in this mapping that I showed. So you have a non-identifiable case. That's why sometimes we have a no answer. Is this clear? Okay. So what are the tools that we have to do causal identification? So this truncated factorization that I showed you, it works in the case of Markovian models, because you see that the variables are all factorized. So the factorization of the interventional distribution is a factorization of every variable given their causes. And since you have all the causes observed, doesn't matter. They are always going to be, any effect is going to be identifiable through this formula. This is called G-computation formula sometimes. The problem gets a little bit harder when you don't have all variables observed. So that's, we need other criterion. So for example, the parent adjustment is the simplest one, you see it. Then we have the backdoor adjustment, is just an improvement in comparison to the parent adjustment. Then we will see the front door adjustment that takes into account a different scenario. And of course, those are all examples, so for specific scenarios, right? But we will also see some tools that are more general. So the calculus is a different calculus that we will have, is extending probabilistic calculus to infer causality. And we also have the identify algorithm that it's equivalent to the applications of the do calculus. So the equivalence between both was shown by the authors of the ID algorithm, but they are both complete for the task of causal identification. We will try to cover all of them. And they are all available in the prose book, the causality book. So let's start. Yeah, so the ID algorithm, there's this reference. I will also give again this reference later. So let's start with the Markovian models. As I said, all you need is the truncated factorization, because then in this scenario, you don't have the U variables here anymore, right? So the truncated factorization reduces to this case where you have only you have our observed cause. And then in this, so this is just the factorization of this PX is a notation for the interventional distribution. So instead of writing here, comma do X, many times you see the subscript is just the same notation when we are denoting the interventional on X. But because of something that we call modularity, we reduce the X is going to, you remove the X from here. So you just can use the observational distribution. So the effect of X on Y can always be written through this formula. So you don't have the do X here anymore, and everything is just the observed distribution. So you can just compute the effect through this formula. Is this clear? You're making weird faces. I think it's not clear. So as I told you, this interventional distribution, as long as so every time that you have a causal diagram, a real causal diagram, right, following the causal functions and confounding and everything, this is going to have it's going to imply a factorization that's every term of this same distribution. So this is just a notation for the same distribution here. This is factorizing according to the causes. And in this case, since I'm the Markovian case, the causes are just observed. So I don't have the use here. And I also have this property that's called modularity, that I can just replace the interventional distribution with the observational distribution. So the truncated factorization is going to be simplified by a product of just observed probability distributions. So you can use this to compute the effect of X on Y. In any case, that's Markovian. So it's always identifiable. Sometimes you call this the G computation. Let's see an example. So as I said, this is always going to be the same formula. So you get the graph. You see there's no bidirected edge here because it's Markovian. Then I can just apply. Here's the product of every variable given the parent. So just factorize following this. And in this case is the joint, right? Probability of X, Y, and Z. If I want just the probability of Y given to X, I can just sum over Z. So here I'm just showing that once you apply the do X, you can also get the manipulated graph. When you apply an intervention, the consequence in the graph is just that you remove the edges into Z. And here you also get the same factorizations. The factorization, you see Z has no parents, and Y has Z and X as parents. So it's here. But in in the end, you get this factorization here. So here it's just the observational joint probability. So the X is going to be removed when you go to the interventional distribution because the probability of X is always 1. So that's the truncated factorization. So you follow this graph, and then you can sum over Z because you are interested in this probability, not in the joint. Okay, so it's simple. You just follow the same formula for any graph, any edge, because it's always identifiable. So when you move to semi-Markovian models, it gets a little bit more complicated, but let's start with the simplest criterion. So assume that you have observed all variables that are cause of X. It's kind of strong, but you have this case of that there's no unmeasured parents of the variable X, which is your treatment. So I have the effect of X on Y is going to be this formula. So you see that's similar to the example that I gave in the previous slide, because once you have the parents, like by the truncated formula, you can just get this. So this follows trivially from the truncated factorization because you have the parents. So this is an adjustment formula. As long as you have the parents, you just put the parents here, and then you see the effect. Let's see an example. So in this example, I can have bidirected edges now, but the parents of X, you don't have bidirected edges in X. So you have all parents observed. So you can just use the parents, and you plug in here. The parents are Z1 and Z2. You plug in here in the where I need parents. So parents, you'll be here, and here. So you plug in on this expression, and this is your expression for the interventional distribution. Clear? Okay, this is nice, but seems very strong as well, because not always I have the parents of X. So what happened then when I have a bidirected edge between X and Z2 in this case? Can I just condition on Z1 and Z2 again? What do you think? So the idea that in these adjustments, I'm trying to remove the confounding effects. So I'm trying to block the influence of every path that's not directed. So this is called confounding path. This is another confounding path. So you have several confounding paths. When I condition on the parents, I'm basically removing the influence because I'm blocking through the separation. Remember, you are conditioning on always non-colliders. But here, once I condition on Z2 and also on Z1, I'm opening, let's see if I have an animation here. Yes. So I'm opening this path because I'm conditioning on Z2. So I make this triplet active. I condition on Z1 again. So I make this triplet active. And this is active again because it's a non-collider. So you have a confounding path inducing association between X and Y. So the expression, if you compute this expression, is going to be not only the direct associated to the directed edge, but also to this confounding path. So this is an unbiased effect. It's not their causal effect. For being causal, we need to block all these confounding paths. And that's how we extend this parent adjustment to something that we call backdoor adjustment. We will see now. So identification via backdoor adjustment is just that you observe. So it's the same question. We have X and Y, and we have the graph. But if there exists a set Z such that Z disseparates X and Y in a graph, that's this graph here. Let's see an example now. I think it's easier to go through the example. So I have this example. It's the same one as the previous slide. So if Z disseparates X and Y in the graph where we have this underline, so it's X underline. So this means that I cut every edge that's going out of X. So it's like, yeah, so it's like removing this edge. So when I remove this edge, you have now these two paths. I have more actually. I have this, I have that, and I have that, 3 paths. So if I have a set Z that disseparates X and Y in this graph, and the set Z includes no descendants, so there's no descendant of X in this set Z, then Z satisfies the backdoor criterion, and then I can have exactly the same formula as before. But as long here Z is no longer the parents, it's just any set that's blocking the confounding paths. So if I have just Z1, you see that if I condition on Z1, I block this path. And I also opened this collider, but I also this other collider is still inactive. So this path is still inactive. Also, this path is blocked because this is a non-collider through this dashed arrow. So you would evaluate that through conditioning on this set Z, all these three paths are blocked. So Z equals to Z1 satisfies the backdoor criteria. So you can just plug in Z1 here and this works. If I have Z1 and Z3 continues to work, you can check later, but you see that opening this collider here doesn't matter because all these two paths are already blocked. But what happened if I have Z1 and Z2, which was the example before? Is this, we have this confounding path that's open, so it doesn't work, right? So I cannot have Z equals to Z1, Z2. What about Z1, Z2, and Z3? It's the same thing, right? So the same path here is open. So knowing the graph allows you to select which variables you should put here in this adjustment formula. So it's not always every set that's going to block your confounding paths. Okay. All right. That is an interpretation of the backdoor adjustment that who have heard about. So who is familiar with the potential outcome framework, first of all? Okay, you. Okay. So maybe you have heard about conditioning ignorability assumption. Have you? No, the other guy. No. Okay, so you are not biased, but that's good because many people in this potential outcome framework, they have this condition as an assumption. So you start the framework saying, assume that you are under this condition. And you look at this expression here and you have no idea what this means. I don't have any idea what this means. It's like just the potential response of Y after an intervention on X is independent of X of the treatments given some set Z. And you give this set Z and you say, okay, this assumption is holding, and then I can continue doing whatever I wanted. But this is easily checked. So there is a theorem that says that this condition holds if the backdoor criterion is satisfied by the set Z. So if you have a graph, you can test. You can get the set Z that you have on hand and check if Z satisfies the backdoor criterion for this pair X and Y. There is an interpretation through a graph that's called counterfactual graph. I don't want to go into details, but it's nice that you know this name. So that is something that we put together, the factual world and also the counterfactual world. So this is the graph as before. You just like copy the same graph, but after an intervention here, and you put them together. There is a procedure to do this. But from this counterfactual graph, you can see if actually the response is independent of X given Z. And you see that it is conditioning on this set Z here. You block these two paths and all the other paths have like a collider, so it's already blocked. So if you have a graph, you can check if independence using potential responses is valid or not. But anyways, the conditioning ignorability, I think that's my note here. If you have heard about it, it's just that this is equivalent to say that the set Z satisfies the backdoor adjustment criterion, okay? The backdoor criterion. If you are in this scenario, then a lot of people are working on estimation of causal effects given such a scenario. So you are in the scenario of backdoor criterion, then you can, your interest now in estimating this expression. So this P, these two probabilities here, sometimes Z is high dimensional. So there are many challenges on how to estimate this in a very nice way. And one of the examples is through propensity score. So basically, so this is just a graph as an example, but you can rewrite the expression. So here I'm just multiplying by 1, right? Because this is just 1. Then in the numerator, I have the joint distribution. And in the end, you are just, you see that the probability in this situation, the interventional probability distribution is just using the joint, but weighted by the inverse of this quantity. And this quantity is called propensity score. So it's the propensity of taking a treatment given some set of covariates. So that's the idea of propensity score. And if X is binary, for example, you can just use logistical multinomial regression. If it's Z is high dimension, you can use some classification approach. If X is continuous, you can use some regression, even machine learning-based regression techniques. So even high dimensional scenarios, you know how to do this pretty well. So once you have this number, you can plug in this estimation in this you can just reweight these probabilities here, and then you see in the next slide the intuition. But remember that this only works, right, if Z is admissible for adjustment. So yes, and then since we are reweighting this, we have this inverse probability weighting technique. So if you have heard, it's basically just reweighting these probability distributions through the inverse of the propensity score. And the idea behind it in inverse probability weighting is that we create a pseudo interventional sample. So imagine that you have this graph, and in this graph, the propensity of X depends on Z, right? So the probability of X and Z is different than just probability of X. So this is not an interventional graph. However, after reweighting with this propensity scores, the inverse of the propensity score, you are going to mimic and minimize the influence of Z. You are kind of going to create a sample where probability of X given Z is going to be equals to probability of X. So imagine here, so suppose that this is your original sample, you have two groups, X is binary, and in blue, I have the Z. So this is just coloring the conditions. So suppose that I have samples that are blue, and the probability of X given Z is 1/4. So I have two samples that are green in the group 0, and the probability of X given Z is 2/3. Once I have now 1 over a probability of X given Z, I'm multiplying this. And then in the end, I'm kind of mimicking a case where I have actually the same number of people that are blue in 0, that are blue in 1, that are green in 0, and green in 1. So I'm balancing, making this sample balanced in the sense that the propensity of receiving the treatment is like uniform. And after this reweighting. So basically, I can just get these weighted samples and apply just sample estimators. So for example, you can get the expectation of Y given to X by just, so you get these samples, then you reweight everything through this estimated propensity scores. And then this is just the sample mean, right? So that's you just count, and then you use this as an interventional sample, experimental sample. So that's the way to do it. If you have if you are interested in the average treatment effect for a binary treatment, it's just the difference of these expectations once you have X, once you have X equals to 0 and 1, right? So you just compute for both, and then you have the difference. So that's all. That's the idea behind inverse probability weighting. How much time I have? Okay. Then so what if backdoor adjustment doesn't work? Suppose I have this graph here. Can you find a set Z that blocks my confounding path? So I am interested in the effect of X on Y. So there is this causal path. I don't mind. There are some mediators here, but what would be the set Z that blocks this confounding path? It's just an edge. I cannot condition on anything there because this confounding path won't vanish. So there is no way to use a backdoor adjustment here. However, there are other ways of doing it. So this is a case where the effect is identifiable, although you have latent confounding. And this is through something that we call front door adjustment. So the conditions are this one. So I need to find a set M which is called mediator set, where the set M intercepts all directed paths from a variable, from any variable X that's in the set X to any variable Y in the set of variables Y. So you need to block all directed paths through this set of mediators. Another condition is that I cannot have unblocked backdoor paths between any of these X's and these M's. So I cannot have a bidirected edge here. So this has to be unconfounded. Then all backdoor paths from M to Y, they have to be blocked by X. So this effect here, the effect of M on Y, has to be identifiable through conditioning on X. So you see that the effect of M on Y has one confounding path, that's this one, but conditioning on X, I block this confounding path. So the effect of M on Y is identifiable as well. And then the expression of the effect is this one. It's basically combining the effect of X on M and the effect of M on Y. So here is the effect of, this is the backdoor adjustment for the effect of M on Y. And then you get this other one to get the effect of M on X, X on M. So in this example, it's simple, right? So it's just the variable M blocks all these directed paths. What about this one? What do you think is the set M? First, is there a set M that satisfies this front door adjustment? You need to block all the directed paths. This is the first requirement. So let's start with M1 and M2. Okay. So I also cannot have any unblocked backdoor path between X and M. So those are like without bidirected edges. So it's fine. What about this effect of M on Y? So these two variables, I have two effects now, but you see that I go one by one. So the effect of M1 on Y, I can block the conditioning path through X. So this is fine. And the other, I can also have this path blocked by just conditioning on X. This other path here is also blocked by conditioning on M, but you look on both at the same time. So M1 and M2 works for this front door adjustment. What about this one? So I have to intercept all. So I have a directed path that's just an edge. So I cannot intercept this. So it doesn't work. And what about this? It's violating some of the conditions. Which condition is it? Yeah, so there is this bidirected edge between X and M, but there's no bidirected edge between M and Y. And this is the directed path. So M is intercepting this directed path. So it satisfying the first. What about the second condition? That is a unblocked backdoor path. So backdoor path is the same as confounding path, is synonym. So that is this path that's entering on X and Y and M at the same time. So this is a backdoor path, and this is unblockable, right? So you cannot block. There's nothing you can do to block this path. And then I cannot apply this. Okay, so there are situations that are still not, that doesn't work with backdoor and front door. And then you go again, let's see another scenario. So there are many scenarios beyond backdoor and front door. So you could have the conditional front door where now you can try to kind of block this backdoor paths between X and M and so on. And then you have a different formula. You could also have something that we call napkin, which is going to give this formula to you. Or you can even have like a completely different graph that's unnamed. Maybe you can put your name here. It's going to be a different formula, right? And it's impossible to treat all this case. So that's why we need something more general. We cannot go one by one. So first, I would like to share with you that there is an app. We can just sign up with your academic email. And this app here, you can basically it can work like ask questions regarding causal inference. So you can draw your graph here, and then you can ask what's the effect of X on Y. And if that is a way to compute, in this case is the backdoor criterion, right? So Z blocks this confounding path, and this is the backdoor adjustment. So causal fusion allows you to just get there's this separation, there's like a lot of things, and identification is one of the tools. So you can get the expression. You can even change the graph and get the front door adjustment. You can get the conditional front door here as well. But in the end, this is using the ID algorithm. So I'm going to tell you in a minute. But in practice, you don't actually derive this case by case. You just draw your graph, and if it's identifiable, you're going to get an answer. If it's not identifiable, it's also going to tell that it's not identifiable. Like this one, it's not identifiable. So you can just, if you just want to see what's the effect and you have the causal diagram, I would recommend you to do this. So as I said, we need general tools. We cannot just do case by case. This would be like infinite types of graph. So Perot developed in 1995 is something that we call do calculus or causal calculus. And it's just extending probabilistic calculus. So it's a way that we detect or identify invariances between the rank 1 of the ladder of causation, which is the observational, and the rank 2 that's interventional of the rank of the ladder of causation. And it's just 3 rules. So those are the 3 rules that we have. The calculus just 3 rules. It seems that is very easy just because it's three rules, but in practice, like you need to kind of have several insights to know how to apply the rules one of the other. And the idea is the goal is to apply these rules until you remove every do operator of your expression, because identifiability gives you an expression that maps the interventional distribution to expression without the do. So if you apply these rules one of the other until you remove all the do's, you get identifiability. And you see that these rules depend on these separations in some manipulated graphs here. So you basically, from the causal diagram, you do the manipulations. I will explain one example, and then from the manipulations, you check if you apply the rules or not. And you can see here, I can exchange a do to an observation of the X. So here I remove the do X completely. Here is just removing observation once I have a do. So this is exchanging the independence, but in the interventional distribution. So let me try to go at least over some examples. So for the rule 1, for example, rule 1 is related to conditional independence in the interventional distribution. And this interventional distribution is, so imagine that this is your causal diagram, and then your G, you need to observe this separation in this manipulated graph GW with a line over W. So this is the upper manipulation. And this upper manipulation will remove every edge that's into, like with an arrowhead into W, which is like this edge here, and also this edge here. So I cut all these edges that are into W. I created this graph, which is the GW bar. And if I observe this separation where Y is independent of, separated from X, given Z and W, so it is correct, right? So I condition on this, and then I have a separation of X and Y. I can condition on W without hurting anything. So this separation is holding in this graph. So this means that I could just do this manipulation here. I can, basically that is this invariance that X is independent of Y, even in the interventional distribution under the W. Okay, so you can apply the rule. So this works if this is observed in this manipulated graph. The rule 2 is related to confounding. So imagine that this is your graph, and the idea is to observe this separation in this graph here. The graph has first a W bar. So the W bar, I remove every edge that's into W here. Then I remove these edges. Then there is the X underline. So that's the lower manipulation. So I remove edges out of X with a tail on X like this. So I remove this. So you see that I end up only with edges that are confounding X and Y. And if Z and W removes every, or like the blocks every of these paths that are left, then I can replace the do X with just observation on X. So this is kind of related to confounded because of this. So once I observe this, I can say that this probability of Y given to W, do X and Z is the same as probability of Y given to X and observation of X and Z. So the action is the same as the observation because you basically removes the problem of the confounding. The rule 3 is related to order. So it's like, you see that I remove the effect of the do X completely. So Y is independent of an action on Z completely. So there is this other graph here. So this is G bar first. So I remove all the edges into W first. So I remove this, that, and that. Then I have to remove this XZ. So this XZ is a different notation here for like all the nodes that are not ancestors of any variable Z in this graph. So I can only remove the edges that are into variables that are not ancestors of the Z nodes. So in this situation, I can remove this edge because X is not an ancestor of Z. So it's fine. I can remove this edge. I can also remove this edge because it's into X. So I remove all the edges into X because X is a non-ancestor of Z. And since I observe now that Y and Z are separate, so you see there's no even path between them, given this in this graph, then this holds. So I can replace. So I can basically say that this quantity is the same as this quantity. So I remove the do X completely from the equation. And it's related to order because I know from here that once I apply an intervention on X, there's no way to affect Y. Y is even before X. So that's why the action on X doesn't affect Y. And then you basically do derivations like that. So this is an example of the front door adjustment. So you see I have like, I apply the probability axioms, then the rules, one after the other, then apply again. So I moved from something that I understand, like it's something that I can just apply the probability axioms, but then I can change one line to another, just applying these rules and arriving on an equation that's not depending on do anymore. It's a do-free expression. So this tells me that the effect is identifiable. So identifiability through do calculus is like, it happens. So it's complete because if I cannot derive a sequence of applications of these rules that gives me this do-free expression is because the effect is non-identifiable. Of course, that deriving this, you never know if you are being like naive and not applying the rules correctly, or it's because the effect is not identifiable. So it's hard. So in practice, people don't actually derive this. It's just educational, I would say. But in practice, people use the ID algorithm. So the ID algorithm does a lot of this. They break the problems in several sub-problems and they solve the problems and then they combine in the end. So if you are interested, just check the paper. This is the paper where was developed the ID algorithm. And then for any graph that you put here, doesn't matter. It's going to give you either a true, it's going to give you a yes or no answer. And meaning that if you have identifiability, you're going to get the expression, the correct expression. Okay. There are many generalizations of the ID algorithm. So this is a paper from 2002. How many time I have? Okay, that's good. So I'm going to now just discuss some generalizations that we have in the field. So first, in the sense of effect identification, we have now cases where we also have available not only observational data, but also experimental data. So how can you put together? And then in the end, you just need an expression that depends only the available distributions. So this experimental data can be randomizing different variables, not necessarily the X that you are interested in. So they have this general identifiability algorithm for like surrogate experiments. So this means randomization of other variables that are not the one that you are interested in. You can do some also counterfactual identifiability from graphs. It is an extension by using the counterfactual graph. So you can check this paper if you're interested on how to do even combining experimental and observational data, counterfactual identification. There's also extension for soft intervention. So here we saw that the manipulation in the model, once you do the intervention, replaces the equation with a constant. So the equation of X was just a constant X. You could just replace with another function. And this is called soft intervention. You just replace, you have a change in the model, but it can be through just a different function. And you have now a calculus for stochastic or soft intervention. So this is extension for this type of interventions. There is also a connection with deep neural networks. The idea is that you leverage, so there's no free lunch again. So you need the causal diagram here as input. You are going to inductive bias using this causal diagram. And then you're interested in one edge specifically. And how you get identifiability is when for any model that is compatible with this structure, you have exactly the same effect. So you do an optimization approach that you get the maximum causal effect that you could have through all these models that are compatible with the structure, and also the minimum of this effect. And you see if the minimum is equal to the maximum. If it's the same, it's because it doesn't matter what's the model that's fit into this graph, you have identifiability. So it's a way to combine, so this paper is explaining how to do interventional identifiability. This is explaining how to do counterfactual identifiability to this reasoning of just comparing the causal effect in all possible models that are fitting to this causal diagram. Some other people are interested in doing bounds of the effect. So sometimes you don't have identifiability, but you could maybe estimate the bound, like a confidence interval. And if this bound is informative in many situations, this is interesting. So there's something that we call partial effect identification. So this is a paper that's doing this. Also, how can we do identification if we don't have the causal diagram at all? So actually, there are several works trying to relax this assumption of causal diagram. This is kind of my field of research. So one of the ideas is, this is not mine, but that's something that we also can do, like in a completely data-driven way. You can find this set Z that satisfies the backdoor adjustment without having a causal diagram. So this is like finding valid adjustment under non-ignorability with minimal DAG knowledge. So basically, they ask questions about order. So you need some type of knowledge. So it's relaxing the assumption of having a full causal diagram. But once you know something related to order, maybe you can use some other techniques to find if a specific set of covariates satisfies your backdoor adjustment. And then in this case, you can apply all these techniques, for example, propensity score estimation and inverse probability weighting and so on, for estimating giving the backdoor adjustment formula. This is another example where you do causal backdoor discovery because you're learning the backdoor set if exists. This is another extension. Sometimes you don't have a way to draw the causal diagram completely, but you can put together variables as clusters of variables, and then you just specify the relationships among these clusters of variables. So it's a way to partially specify the model, right? So you have a coarser specification of the model. And this paper, for example, extends every tool that you need, the separation, causal YD algorithm and everything, once you have this type of representation of the model. Also, you could have as well as input a peg. So yesterday you learned only from data this representation of a Markov equivalence class. And there are several tools that allow you to do effect identification when you only have this representation. The first, so this is like can be constructed in a fully data-driven way, right? And the first extension in this direction was by Perkovic and others. She extended the backdoor. Actually, it's a general adjustment criterion. It's an extension of the backdoor. There was another paper before her that extended the backdoor. So there's the generalized backdoor criterion, and this is the generalized adjustment criterion, but it's similar. You in the end have this formula. So this is the adjustment formula, and you detect through this paper here. You can identify if the effect is identifiable through adjustment or not. But you know that adjustment is not complete. So we also extended, so this is one of my works, where you can have a peg that the effect can be estimated if you have identifiability through any formula. So we extend actually the ID algorithm. So this is called ID for pegs, or conditional ID for pegs. So this algorithm allows you to just input any peg here. And as long as the effect is identifiable, it's going to give you an expression, can be very different from the adjustment. So you can do this in a completely data-driven way. So this package is available in my GitHub if you want to use. And what is the meaning of identifiability in a peg? So a peg is a class, right? So now we don't even look on regardless of the model that's agreeing with a causal diagram. We need now to, regardless of the model that's agreeing with all the models inside of the Markov equivalences class. So it's a bigger class. But the idea is like, doesn't matter what's the causal diagram inside or the graph that's inside of this Markov equivalence class, the effect is going to be identifiable exactly through the same expression. So if you have this case, then you have identifiability from the Markov equivalence class. So this is an example where the effect is identifiable through backdoor. You can see that two different I actually have to enumerate all of them to check through enumeration, but there's proofs that's showing that it would work for any graph. But in this case, every graph has the same expression for identifiability. And no identifiability, you only need one, right? So you could have cases where the effect is identifiable, but if that exists, it's like any other graph where either the effect is not identifiable or is identifiable through a different expression, you would have no identifiability, right? So this is an example where you could construct this case and then you don't have a way to do adjustment anymore. So you have no identifiability there. So this is kind of a summary of everything that we are like the vision of the field, I would say. So you have the structural causal model as the nature, but usually it's an observed. And from this, you have implied many objects. You have data, you have sometimes prior knowledge. You can do through learning, you can have like causal discovery. So the goal here is like, how can I combine everything that I know coming from data, coming from knowledge, I don't know, but how can I have like a representation of my knowledge encoded using graphical language? So this we saw yesterday, right? So this was causal learning, B here, causal learning. And then so today we saw a little bit about how can, from this representation, doesn't matter which type of representation, so we are working on relaxing this, on answering different questions, but we are here in inference. How can I answer questions regarding a probability, intervention of probability distribution? Of course, I have cases where there's no answer. So something that I haven't talked here, something about causal experimental design. You could then try to design experiments, could be just observing new variables, running experiments, randomized experiments, but which is the best or the optimal approach to when I go back to the loop, I have something that maybe is answerable. Also, once I have an answer, we are, of course, everything here is statistics. So validation is important. And once this becomes a discovery, this has to go back as knowledge. So there is a loop that actually is trying to mimic the scientific discovery of the process of scientific discovery. What else I have here? Yeah, so we saw this too today, but there are many other things that maybe we will see in the next two lectures. So what are the current challenges and open problems? First, effect identification in more general equivalence classes. So yesterday we saw how to go beyond the equivalence class, and this the last algorithm that I told you, it's assuming that you have a Markov equivalence class. So it's equivalence class coming only from observational data. So once you have more knowledge, more experimental data, the algorithm doesn't, at least is not proven to be so sound, right? So you need other algorithms to do this in more general equivalence classes. Scalability is always a problem. So how can you do identification without maybe learning or learning the entire peg or construct the entire causal diagram? Sometimes you're just interested in one edge. Why I need to learn the full graph to have just the effect of one edge? Maybe I can construct the graph in an adaptive way or have approaches that maybe are more goal-oriented, right, in this direction. Causal effect estimation for general identification formula. So a lot of people, I would say 99% of them, are working on the estimation of the backdoor formula, the backdoor adjustment, assuming either conditioning ignorability, assuming that you run the backdoor criteria at least and estimate and got the covariate, the set of covariates. But how can you do this for any of those variables? This can be very complicated. Causal experimental design is something that I haven't discussed, but it's a challenge, especially in the situation where you have latent variables. And effects among abstractions. So the paper that I showed you is doing this already, but how can you connect maybe with causal representation learning and other types of doing causal abstraction? So there are several limitations there. And the last one that I want to say is continue causality again, because last time I showed you that it would be important to do this process of causal discovery through continual learning, but integrating learning and effect identification at the same time is also something interesting, because it kind of allows you to do this type of adaptive and goal-oriented approach. Yeah, so that's all from my side. I guess I think I have again a tutorial. So if you want to run, there's a Google Colab there. You, of course, can just reach me through email, or I'm really available if you have questions or discuss about the topic. Thank you, everyone. If you have questions, please ask them now. Thank you. All right, questions. It was too hard today. No. All right. Okay. So tomorrow is going to be a completely different topic, very exciting because it's new. It's causal representation learning with Dev. So I'm really looking forward to it. So see you tomorrow.